Welcome back to AI.Code.Cast. Today, we're going to be taking a deep dive into a classic coding problem. One that really gets those algorithmic gears turning, right? The single number problem.
Oh, yeah. Yeah, it's a favorite for a reason. It's deceptively simple at first glance, but it offers like a surprising amount of depth when it comes to, figuring out solutions.
Exactly. So, for our listeners out there, just imagine you're given like a list of numbers, right? Where every single number appears twice, except for one,
Hmm.
like one lone wolf.
Yeah.
And our mission, to track down that unique number. But here's the kicker. We need to do it like as efficiently as possible.
Yeah, efficiency is key here.
We're talking like a solution that ideally runs in linear time
Mhm.
and only uses a constant amount of extra space.
That's where the real fun begins, right? It's
Yeah.
finding a needle in a haystack, but you also got to be super careful about how much energy you're using to search.
Yeah, you don't want to like make a mess while you're searching.
Exactly. We want to find that needle quickly, but without creating a computational avalanche.
Right, so no bulldozing through this with brute force. Speaking of, how would we even go about brute forcing this problem?
Well, imagine you just start picking numbers from the list. At random, right.
Yeah.
You pick one, and then you got to compare it to every single other number in the
I
list
Okay.
to see if you find a match. If you don't find a match, you know you found your lone wolf.
Okay. I mean, it makes sense at like a basic level, but I can already see how that could get really messy really quickly.
Absolutely. Especially if you're working with a massive list, you end up doing tons and tons of comparisons.
Yeah, you're basically comparing every number to every other number.
Exactly. And as your list grows, the number of comparisons you got to do, it just skyrocket.
It explodes.
Yeah, it explodes. And we're talking about a runtime complexity of big O of n squared.
Oh, okay.
Which basically means the time it takes to solve the problem increases exponentially. As the size of the list increases, it just doesn't scale well.
Yeah, no, that makes sense. So, okay, back to our constraint then. We need a solution with linear runtime complexity. So, the time it takes should increase like proportionally to the size of the list, not exponentially.
Right.
And we need to use like constant extra space too.
Right. We can't afford to be creating these massive temporary data structures,
Hmm.
ones that just keep growing and growing along with the list.
Okay, so what's a smarter way to tackle this then?
Well, one approach that often comes up when you're dealing with searching and counting is the trusty hash table.
Ah, yes, the hash table.
Yeah.
Our reliable friend. You think about it, it's like a really well-organized filing cabinet where you can just instantly find whatever information you need.
Precisely. In this case, we'd be using the numbers from our list as the keys in our filing cabinet, and we'd be storing how many times we've seen each number as the values.
Okay, I'm not following.
So, let's say we encounter the number 5 twice in our list. Our hash table would have an entry for 5,
Mm-hmm.
and the value associated with that entry would be...
So it'd be like 5, too?
Yeah, exactly.
Okay.
5, 2. Perfect.
Yeah.
And then, once we've gone through our entire list and built up our hash table, all we got to do is scan through it.
Uh-huh.
We're looking for the key that has a value of 1.
Gotcha. Okay, so that would be our unique number then.
Exactly.
This definitely feels like way faster than like the brute force approach.
Oh, absolutely, because you're no longer comparing every single number to every other number, right?
Right.
On average, looking something up in a hash table takes constant time.
Constant time.
Yeah, we call it big O of 1,
Uh-huh.
which means the time it takes to find what you're looking for in that hash table stays pretty much the same, no matter how massive the table itself gets.
That's amazing.
It is. But, there's always trade-offs in computer science.
Right. I was going to say, there's got to be a trade-off.
You're sharp. You're absolutely right. There is a trade-off.
Okay.
And that trade-off comes in the form of memory.
Uh-huh.
We are using extra memory to store our hash table. And, unfortunately, the size of that table, it's going to grow proportionally to the size of our list.
Right. So the bigger the list, the bigger the hash table.
Exactly. So in terms of space complexity, we're talking about big O of n, which means the memory we're using grows directly in proportion to the number of elements in our list.
Okay. So it's speed for space.
Classic trade-off in computer science. You got it.
But I'm curious, are there any other approaches? Maybe something that strikes a different kind of balance between these factors.
You're thinking like a true computer scientist. And yes, there are. Do you remember how we talked about that brute force approach?
Yeah.
Just grabbing random numbers and comparing them? What if, instead of that chaos, we tried to bring a bit more order to the situation?
Okay, I like where this is going.
Like, what if we sorted our list first?
Oh, interesting.
Yeah, this is the what we call the sort then linear scan approach. It's kind of like tidying up a really messy room before you start looking for something,
Mhm.
right?
Right, right. So if we sort the list first, then all of the identical numbers will end up right next to each other.
Precisely. They'll be all grouped up, which makes it way easier to spot the one that's different, the one that's on its own, and
And we can just go through the list one by one and just see if there's any mismatches.
yeah,
And then, boom, that's our number.
you got it. You see how intuitive this feels? Like you don't need any fancy data structures or anything.
Right. It's a very, like, elegant, simple solution.
Yeah.
But I'm thinking, how efficient is this?
Good question, good question. So the scanning part, that's pretty efficient because you're only going through the list one time.
Right.
So that gives us linear time, which is big O of n. The hiccup is the sorting itself.
Ah, yeah.
Sorting algorithms, they typically take what we call O of n log n time,
Okay, right.
which basically means the time it takes to sort grows a bit faster than linear time, but not as crazy as that n squared we saw with the brute force.
Okay, so it's a bit of a compromise then.
Right. It's a compromise. Like we're trading a bit of speed for simplicity.
Right. Okay, so we've got, like, brute force, which is, like, the easiest to understand,
Mm.
but it's very inefficient. Then we've got the hash table, which is fast, but we're using extra memory. And then the sort and scan, which is, like, kind of right in the middle.
Yeah, you're starting to see those trade-offs, right?
I am. And you know what I'm thinking? I'm wondering if there's a way to solve this problem where we don't have to loop through the list at all.
You're thinking like a true algorithmic innovator. And you know what? There actually is a pretty cool mathematical approach that might just surprise you.
Okay, I'm all ears. This sounds exciting.
It plays on the fact that we know only one number in the list is unique, and all the others show up exactly 2 times.
Oh, yeah.
So what if I told you we could find our unique number using a super clever formula based on, like, summing the elements with duplicates and summing, without duplicates?
Okay, this sounds interesting, but also kind of mind-bending.
It is. It is. But it's a lot simpler than it sounds once we unpack it.
Okay, so walk me through it. How do we even get started with this?
All right, so let's say we've got a list like 1, 2, 2, 3, 3. First, we just sum up all the numbers in the list. Easy peasy.
So 1 plus 2 plus 2 plus 3 plus 3.
Yeah, which gives us
11.
11. Perfect. Now, for the next part, we need the sum of all the unique numbers in the list.
Okay, wait, but how do we get that cleverly? Like, without actually picking them out one by one?
Ah, excellent question. We could use what's called a set for that, which, by its very nature only keeps unique elements. But we could also explore some other methods later on if you'd like to dive into that.
Okay, we can save that for later then.
Yeah, yeah. So for now, let's just assume we have both sums, right? The sum of all the numbers and then the sum of just the unique ones.
Okay, so we got 11 for all of them.
Mm-hmm.
And then for the uniques, we've got 1 plus 2 plus 3, which is 6.
You got it. 11 and 6. Now comes the cool part. We use this really simple formula. 2 times the sum of the unique numbers minus the sum of all the numbers.
Okay, I'm following.
So in our case, that would be 2 times 6
12.
minus 11.
Which equals 1.
Mm-hmm.
And 1 is our unique number.
Boom! There it is. We used math to find our lone wolf.
That's so cool. It's like we're using the difference between these two sums to isolate that single number.
Exactly.
But how efficient is this, like, in the grand scheme of things?
That's a really good point to bring up. So while it is a clever solution, there is some overhead. Like, even though we're not directly going through the list in a loop, we still got to calculate those sums, right? Which means looking at each element at least once.
Yeah.
So we're looking at a time complexity of O of n, still linear, which is good.
Okay.
But then remember, we might be using a set to figure out the sum of the unique numbers.
Right.
So that adds a little bit to our space complexity. So in terms of efficiency, it's, on par with the hash table O of n for both time and space.
Okay, so not as, like, magically efficient as it might seem at first glance.
Right. But it's definitely a more creative, outside-the-box way of thinking about the problem.
I love how it takes advantage of the specific, like, rules of our problem. Like,
Yeah.
the fact that there's only one unique number. That's really neat.
It is. It is. But you know what? You want to hear about a method that's even more efficient.
There's another one.
There is. And it just might be the most elegant solution yet. We call it bit manipulation using the XOR operation.
XOR. Now, that sounds familiar. Like, from way back in my computer science class.
It's a good one. It might seem intimidating at first, but I promise it's not that bad once we break it down.
Okay, good. Because to be honest, I need a bit of a refresher on XOR. What is it exactly?
So XOR stands for exclusive OR, and it's a bitwise operation, which basically means it works on the individual bits of numbers, comparing them one by one.
Okay, yeah, that's starting to come back to me.
Good, good.
But how does this help us solve our problem?
Well, XOR has these two really cool properties that make it perfect for this. The first one is any number XORed with itself will always result in 0. Think of it like a light switch. If you flip it twice, you end up back where you started.
Right. So 5 XOR 5 equals 0.
You got it. Now, the second property, this is crucial. Any number XOR with 0 will just stay the same. So, like, 5 XOR 0 just equals 5. And that's what lets us isolate our unique number.
Okay, I'm intrigued, but I don't quite see how we get to the solution yet.
Right, so picture this. We take all the numbers in our list and we XOR them all together, one after the other.
Okay.
Now, because every duplicate number appears twice, right, their XOR operations are going to cancel each other out.
Because of that first property. A number XORed with itself is 0.
Exactly. And then because of the second property, the unique number, well, that's just going to be XORed with a bunch of zeros, and it'll stay unchanged.
So it's like all the duplicates just vanish.
Yeah.
And the unique number is the only one left standing.
Exactly. It's like magic, right? But it's actually just beautiful, elegant logic at the bit level. Want to see this in action? We can walk through an example.
Absolutely. Let's see how this XOR magic works.
Okay, so let's take that same example list, 1, 2, 2, 3, 3. But this time, instead of adding them up, we're going to XOR all these numbers together, one by one.
All right, so we'll start with 1 XOR 2, which gives us 3, right?
3, you got it.
Okay, then we take that 3 and we XOR it with the next number in the list, which is 2. So 3 XOR 2, that should give us 1.
1, that's right.
Okay, and then we take that 1 and XOR it with the next number, which is 3.
Keep going, keep going.
So 1 XOR 3, that's 2, I think.
2, yes, you're getting it.
Okay, and then finally, we take that 2 and XOR it with the last number in the list, which is, again, 3.
Right.
So 2 XOR 3, and that brings us back to 1, our unique number.
See? It works.
I gotta admit, seeing it like that step by step really makes it click.
Yeah, it's cool, right? It's like all those duplicate numbers, they just kind of, poof, disappear.
They cancel each other out. It's amazing how something that seems, kind of complex at first, like bitwise operations, can actually lead to such a simple and elegant solution.
It is. It is. Elegance through simplicity. That's what we aim for.
Right. But speaking of elegant, how does this XOR approach, how does it measure up when it comes to efficiency?
That's the beauty of it. We're only going through the list once to do all those XOR operations. So the time complexity, a very efficient O of n, linear time, baby.
Nice.
And get this, we're not using any extra data structures, no sets, no hash tables, nothing. So the space complexity, a beautiful O of 1, constant space.
Wow. Okay. So it's the fastest and the most space-efficient solution we've talked about so far?
It is.
I mean, it seems almost too good to be true. Are there any, catches, any gotchas we need to be aware of?
Well, there is one important thing to keep in mind. This XOR magic, it only works if we're absolutely sure that there's exactly one unique number and all the other numbers appear exactly 2 times.
Okay. Yes.
If we had 2 unique numbers or if some numbers appeared, 3 times or more, then this approach wouldn't give us the right answer.
Right. That's a bit of a specialized tool.
Yeah, it is. But when you can use it,
Yeah.
it's super powerful.
So it really goes to show that you need to really understand a problem and its constraints before you jump into a solution, right?
Absolutely.
Like in this case, knowing that we needed linear time and constant space complexity, well, that kind of helped us narrow down our options.
Right. It did. It did. It's like, imagine you're going on a day hike, right? And you need a backpack. But you wouldn't bring a huge heavy-duty camping backpack for just a day hike, would you?
No way. You want something light and efficient.
Exactly. The right tool for the job.
Right. So in this case, the XOR solution, that's our lightweight backpack for this particular problem.
It is. And it's not just about knowing all these different approaches, It's about knowing when and how to apply each one effectively. That's what separates a good programmer from a truly great one.
Okay, so to recap for everyone listening, we've gone over, 4 different ways to solve this single number problem?
We have.
We started with brute force, which is, simple but not very efficient. Then we looked at hash tables, which are super fast, but they do use some extra memory. Then we talked about sorting the list and then scanning through it, which is like a nice balance of simplicity and speed.
It is.
And then finally, we dove into the world of bit manipulation and discovered the magic of the XRR solution.
The most elegant of them all.
It really is.
Yeah.
What was the biggest takeaway for you during this whole exploration? What stood out to you?
I think for me, the most insightful thing is that there are almost always multiple ways to solve a coding problem. And the most obvious solution, it might not be the most elegant one or the most efficient one. Sometimes you got to get a little creative.
Yeah, and sometimes the journey of like exploring all those different approaches, well, that's just as valuable as actually finding the answer.
Yep.
So
It is. It is. Because it makes you really understand the problem from all these different angles.
it does. It does. And it gives you more tools to add to your toolkit as a programmer. So where does this leave our listeners? What should they take away from this deep dive?
I think the key takeaway here is to really understand what the problem is asking for and then look at those constraints. Like in this case, we needed linear time and constant space complexity.
Right. So those constraints can really help guide you toward the best solution.
Exactly. Like they can help you rule out certain approaches from the get-go.
Okay, so it's not just about knowing the algorithms. It's about knowing when to use each one.
You got it.
And that's what makes a good coder a truly great one.
It really is. Like it's amazing how such a seemingly simple problem can have so many different solutions.
It is. It really highlights like the beauty of algorithmic thinking, right? Like
Yeah.
you can approach the same problem from all these different angles.
Exactly. And sometimes the most elegant solution, well, it's not the one that you immediately think of.
Right, right. Sometimes it takes a little creativity, a willingness to think outside the box, maybe.
I think that's a great lesson for anyone, not just programmers. Like
Yeah.
sometimes the best solutions come from challenging those assumptions.
Yeah.
Looking at things from a different perspective.
Totally. So as we wrap up our deep dive into this single number problem, what are some like key takeaways you'd like our listeners to walk away with?
I'd say one of the most important things to remember is there's no one right way to solve a coding problem. Like the best approach, it often depends on those specific constraints you're dealing with.
Right. The concern.
Yeah, like is it time complexity that's the biggest concern? Or space complexity? Or maybe it's like how readable and maintainable your code is.
Right, right. It's about picking the right tool for the job, essentially.
Exactly. You hit the nail on the head. It's like you wouldn't use a hammer to tighten a screw, right?
No, definitely not.
Each tool has its own strengths, its own weaknesses, and it's really up to you as the programmer to choose the one that fits best.
So it's not just about knowing the algorithms. It's about knowing how to apply them in the right situations.
You got it. And, sometimes the journey itself, like exploring all those different tools and techniques, that's just as valuable as the solution itself.
Yeah, I totally agree. It helps you learn and grow as a programmer. And who knows, maybe one of our listeners will come up with an even better solution to this single number problem, something we didn't even talk about.
Wouldn't that be cool? That's what I love about computer science. There's always room for innovation, always something new to discover.
Absolutely. So to all our listeners out there, keep those minds sharp, keep coding, and keep exploring. Thanks for joining us on this deep dive. We'll see you next time on AI.Code.Cast.